the eternal flame. Long before Rome rose to conquer the Mediterranean world, before the Greeks carved their philosophies into marble temples, a mountain stood in the Tyrrhenian Sea, breathing fire into the night. The ancient mariners who ventured across these waters knew it by many names, but they all understood one fundamental truth. This was no ordinary island. This was Stromboli, and it had been burning since the dawn of human memory. The island emerges from the sea like a perfect cone, its slopes rising dramatically from the dark blue waters to a summit perpetually crowned with smoke. At just 3 square miles, Stromboli is barely a speck on any map of the Mediterranean. Yet its presence has loomed large in human consciousness for millennia. The Greeks called it one of the homes of Aeolus, god of the winds, believing the volcanic activity was caused by divine breath escaping from caverns beneath the earth. Later, they would associate it with Hephaestus, the blacksmith god, convinced that the regular explosions were the sound of his hammer striking anvil as he forged weapons for the immortals. But Stromboli needed no mythology to be remarkable. Every 15 to 20 minutes, with a regularity that has astonished geologists for centuries, the volcano erupts. Not in the catastrophic manner of Vesuvius or the apocalyptic fury of Krakatoa, but in modest, rhythmic bursts that send fountains of incandescent lava arcing into the sky. This phenomenon is so distinctive, so uniquely characteristic of this particular mountain, that volcanologists around the world now use a single word to describe any volcano exhibiting similar behavior: Strombolian. For at least 2,000 years, and quite possibly much longer, this pattern has continued without significant interruption. Roman historians documented the volcano's activity, describing how sailors used its glow as a navigation beacon, calling it the Lighthouse of the Mediterranean. The reliability of its eruptions made it more dependable than any human-made lighthouse could ever be. In an age before GPS, before radio, before even the magnetic compass was widely used in European waters, Stromboli stood as a pillar of fire by night, guiding ships safely through the darkness. The island's human inhabitants have always been few. Today, perhaps 400 souls call Stromboli home, living primarily in small villages on the northeastern coast, as far from the active craters as the limited geography allows. These communities cling to the slopes, their white houses cascading down toward the sea, connected by narrow pathways too steep for vehicles. Life here has always demanded a peculiar form of courage, a willingness to coexist with forces that could, without warning, turn deadly. Yet generation after generation has chosen to stay drawn by the extraordinary richness of the volcanic soil, the abundant fishing and the surrounding waters, and perhaps something less tangible, the magnetism of living at the very edge of Earth's restless power. The geology beneath Stromboli tells a story written over hundreds of thousands of years. The island sits along a volcanic arc stretching from the Bay of Naples to Sicily, a consequence of the African tectonic plate sliding beneath the Eurasian plate in a process called subduction. As the African plate descends into the Earth's mantle, it carries with it seawater and sediments which lower the melting point of the surrounding rock. This creates magma, which rises through weaknesses in the overlying crust, eventually breaking through to the surface. Stromboli is one of several volcanoes born from this process, part of a chain that includes the infamous Vesuvius and the volatile Mount Etna. What makes Stromboli unique, however, is not its origin but its behavior. The magma beneath this particular volcano is relatively low in silica content, making it quite fluid compared to the thick, viscous magma found in more explosive volcanoes. This fluidity allows gases dissolved in the magma to escape relatively easily, preventing the buildup of pressure that leads to catastrophic eruptions. Instead, gas bubbles rise steadily through the magma column and burst at the surface in those characteristic regular explosions, like a pot of sauce gently simmering on an eternal stove. Scientists believe Stromboli's continuous activity may have persisted for at least 20,000 years, making it one of the longest-lived eruptions on Earth. The volcano maintains at least 3 active vents at its summit, each contributing to the ongoing display. The eruptions follow a remarkably consistent pattern. Gas-rich magma rises to the surface. The pressure releases in an explosion that throws molten rock several hundred feet into the air. Then the system resets and begins again. This cycle has been so reliable that researchers have used Stromboli as a natural laboratory, studying it to understand volcanic processes that remain hidden in more dangerous or inaccessible volcanoes worldwide. Yet reliability should never be confused with predictability. and constancy should never breed complacency. For all its rhythmic regularity, Stromboli remains a volcano. And volcanoes are ultimately expressions of forces beyond human control or complete understanding. The same mechanisms that create those mesmerizing fountains of fire every quarter hour are capable, under certain conditions, of producing something far more dangerous. The island's history is punctuated by moments when the gentle rhythm broke, when the volcano reminded its human neighbors that they live not beside a tourist attraction but atop a geological titan that had been old when their civilizations were young and would continue burning long after those civilizations had turned to dust. The people of Stromboli have always lived with a particular awareness that sets them apart from inhabitants of more stable lands. They know the mountain's moods, can read its temperament in the color of the smoke, the frequency of the explosions, the smell carried on the wind. This knowledge, passed from grandparent to grandchild, is not written in any textbook, but etched into the collective memory of a community that has survived by learning to listen when the mountain whispers. In the ordinary course of things, Stromboli's eruptions pose minimal danger to the villages below. The prevailing winds typically carry ash and debris away from inhabited areas, down the northwestern slope known as the Sciara del Fuoco, the stream of fire. This natural channel, a steep scar carved into the volcano's flank by centuries of rockfalls and lava flows, serves as a kind of safety valve, directing most of the volcano's violence harmlessly into the sea. The villages, nestled on the opposite side of the island, have historically enjoyed a degree of protection that made coexistence with the volcano not just possible, but almost comfortable. But the mountain does not always whisper. Sometimes it shouts, and when it does, the consequences can be swift and terrible. The historical record, fragmentary though it is for earlier centuries, reveals moments when Stromboli exceeded its normal bounds. In 1919, 4 people died when the volcano produced a particularly violent explosion, hurling massive blocks of rock far beyond their usual landing zones. In 1930, another paroxysmal eruption killed several more, demonstrating that the volcano's gentle reputation could shift in an instant. These larger eruptions, termed paroxysms by volcanologists, represent a dramatic escalation from Stromboli's baseline activity. Rather than the modest bursts that characterize normal, Strombolian behavior, paroxysms involve the sudden release of far greater volumes of gas and magma, producing eruption columns that can reach thousands of feet in height and ejecting volcanic bombs that weigh hundreds of pounds. The mechanism behind these events has long puzzled scientists. Why does a volcano famous for its regularity occasionally break its own pattern so dramatically? Modern research suggests that paroxysms occur when deeper, more gas-rich magma suddenly rises through the volcanic system, encountering and mixing with the shallower magma that feeds the normal activity. This interaction can trigger a cascade effect, releasing gases that had been trapped at depth and producing an explosion orders of magnitude more powerful than the regular eruptions. The problem from a hazard perspective is that these events can occur with little warning. The precursors, if they exist, are often subtle and difficult to distinguish from the volcano's constant background noise. The year 2002 brought this danger into sharp focus. On December 28th, after several days of increased seismic activity that many residents barely noticed amid the volcano's perpetual rumbling, Stromboli produced 2 major landslides. Portions of the Sciara del Fuoco collapsed, sending approximately 15 million cubic meters of rock and debris cascading into the sea. The landslides generated tsunamis that struck the island's coastline within minutes, waves up to 30 feet high that damaged buildings and boats in the harbor. Miraculously, no one died, but the event served as a stark reminder that Stromboli's threats extend beyond the summit eruptions. What made the 2002 event particularly alarming to scientists was its demonstration of how interconnected volcanic hazards can be. The landslides occurred during a period of heightened eruptive activity, suggesting that increased magma movement at depth had destabilized the volcano's steep slopes. The Sciara del Fuoco, that natural drainage channel that usually protected the villages, had revealed itself as a potential source of danger. If enough material collapsed into the sea in a single massive failure, the resulting tsunami could be catastrophic not just for Stromboli but for coastal communities throughout the southern Tyrrhenian Sea. Following the 2002 crisis, Italian authorities significantly expanded monitoring efforts on the island. The Istituto Nazionale di Geofisica e Volcanologia, Italy's National Institute for Geophysics and Volcanology, established a comprehensive network of sensors around Stromboli. Seismometers track ground vibrations, thermal cameras monitor the summit craters, GPS stations measure ground deformation, and gas sensors analyze the chemical composition of volcanic emissions. This data streams in real time to monitoring centers on the Italian mainland, where teams of volcanologists watch for any deviation from normal patterns that might herald a larger event. Yet for all this sophisticated technology, prediction remains elusive. Stromboli as continuous activity creates a kind of background noise that makes it extraordinarily difficult to identify the subtle signals that might precede a paroxysm or landslide. It is rather like trying to hear a whisper in a room where someone is constantly talking. The mountain never goes silent, never provides that baseline of quiet against which changes become obvious. Every measurement must be interpreted against the context of ongoing eruption, and the line between normal variation and dangerous escalation is often maddeningly unclear. The residents of Stromboli have adapted to this uncertainty in ways both practical and philosophical. Civil protection protocols dictate evacuation zones and procedures, though in practice, many islanders regard some of these measures with a certain fatalism born of generations spent in the volcano's shadow. They have witnessed false alarms and near misses, have seen scientists express concern that led to nothing, and have experienced sudden violence that no one predicted. This breeds not exactly complacency, but rather a pragmatic acceptance that some risks cannot be eliminated, only endured. Tourism has complicated this ancient relationship between people and volcano. Stromboli has become a destination for travelers seeking the thrill of witnessing active volcanic eruptions up close. On summer evenings, guided groups climb to viewpoints near the summit, watching the explosions against the darkening sky, photographing the arcs of molten rock with smartphones and cameras. The volcano that once served as a beacon for sailors now draws visitors from around the world, their economy sustaining the island's small population in ways traditional fishing and agriculture no longer can. This transformation has created tensions that simmer beneath the surface of island life. The volcano is simultaneously a source of livelihood and an existential threat, a natural wonder and a potential killer. Each explosion delights tourists and reminds locals of their vulnerability. Every seismic tremor recorded by monitoring stations must be weighed. Is this the normal background activity, or is it the beginning of something worse? The architecture of fire. Beneath the deceptively simple cone of Stromboli lies a complex plumbing system that has taken hundreds of thousands of years to evolve. Understanding this subterranean architecture is essential to comprehending why the volcano behaves as it does, why it maintains its rhythmic eruptions with such consistency, and why that consistency can occasionally give way to something far more dangerous. The magma that feeds Stromboli originates at depths of approximately 60 to 80 miles beneath the Earth's surface, in a region where the descending African plate releases water and other volatiles into the surrounding mantle rock. This process lowers the melting temperature of the rock, creating pockets of molten material that are less dense than the solid rock surrounding them. Like oil rising through water, this magma begins its long journey upward, driven by buoyancy and the immense pressures of the deep earth. As the magma ascends, it accumulates in what geologists call a magma chamber, a region of partially molten rock situated perhaps 2 to 3 miles beneath the summit. This is not a hollow cavern filled with liquid rock, as popular imagination might suggest, but rather a zone where hot magma exists within a matrix of solid and partially melted rock, rather like a sponge saturated with water. The magma chamber acts as a staging area, a place where rising magma can accumulate, cool slightly, and undergo chemical changes before continuing its journey to the surface. From this chamber, narrow conduits extend upward toward the summit craters. These pathways, only a few yards in diameter, are the final channels through which magma must travel to reach the surface. The geometry of these conduits plays a crucial role in determining the style of eruption. In volcanoes with very narrow or twisted conduits, magma movement becomes restricted, allowing pressure to build until it releases catastrophically. Stromboli's conduits, however, appear to be relatively open and straight, permitting the steady rise and degassing of magma without the accumulation of dangerous overpressure. The magma itself is basaltic in composition, rich in iron and magnesium, relatively poor in silica. This chemistry determines its physical properties, particularly its viscosity. Stromboli's basaltic magma flows with relative ease compared to the thick, pasty magmas found in more silica-rich volcanoes like Mount St. Helens or Pinatubo. This fluidity has profound implications for eruptive behavior. When gases dissolved in the magma begin to exsolve and form bubbles as the magma rises and pressure decreases, these bubbles can rise through the liquid relatively easily, coalescing and growing as they ascend. The regular eruptions that define Stromboli's character are essentially the result of large gas slugs rising through the magma column and bursting at the surface. Imagine a bottle of champagne, but one where the bubbles are enormous, each one perhaps several yards across. As these massive gas pockets rise through the final hundreds of feet of the conduit, they accelerate, reaching speeds that can exceed 60 miles per hour. When they burst through the surface, they fragment the surrounding magma into spray and clots, hurling it skyward in those characteristic fountains of fire that occur every 15 to 20 minutes. This process, termed gas slugging by volcanologists, is remarkably stable when conditions in the shallow plumbing system remain constant. The formation and rise of gas slugs becomes almost rhythmic, creating the pattern that has characterized Stromboli for millennia. But this stability depends on a delicate balance of factors: the rate at which new magma arrives from depth, the efficiency of degassing, the geometry of the conduits, and the properties of the magma itself. When any of these factors changes significantly, the system can shift into a different mode of behavior. An increase in the magma supply rate from depth can overload the normal degassing mechanisms, allowing pressure to build. A change in magma composition, perhaps from the arrival of a fresh batch of magma from the deeper chamber, can alter viscosity and gas content. A partial blockage in one of the conduits can redirect magma to another pathway or cause pressure to accumulate behind the obstruction. Any of these scenarios can trigger a paroxysmal eruption, those sudden violent events that dwarf the normal activity. The three active vents at Stromboli summit, located within a crater terrace on the volcano's northwestern flank, each connect to the underlying conduit system, but may tap into it at slightly different depths or locations. This means they can behave somewhat independently, with one vent erupting while the others remain quiet, or all three participating in a coordinated display. The vents themselves are constantly evolving features, growing, shrinking, and occasionally being buried or reopened by the accumulation and removal of volcanic debris. Monitoring these vents and the processes occurring beneath them requires a combination of techniques. Seismic instruments detect the vibrations caused by magma movement and gas slug formation. These signals have characteristic patterns. The formation of a gas slug produces a specific type of seismic tremor, while the slug's passage through the conduit creates rhythmic pulses, and its explosive bursting at the surface generates sharp, high-frequency signals. By analyzing these seismic waves, scientists can effectively listen to the magma plumbing system, inferring what is happening hundreds or thousands of feet beneath the surface. Thermal monitoring adds another layer of understanding. Infrared cameras trained on the summit craters continuously measure the temperature of exposed magma and the heat flux from the vents. Changes in these thermal signatures can indicate shifts in the magma supply rate or the level of magma within the conduits. During periods when magma rises higher in the system, the vents become hotter and brighter. When the supply decreases, they cool and dim. Gas measurements provide yet another window into the volcano's internal state. The volcanic gases that vent continuously from Stromboli's summit consist primarily of water vapor, carbon dioxide and sulfur dioxide, along with smaller amounts of other compounds. The ratios of these gases reflect conditions at depth, particularly the pressure and temperature at which the gases exsolve from the magma. By analyzing gas composition, scientists can infer whether the magma currently feeding the eruptions has recently arrived from the deep chamber or has been residing at shallow levels for an extended period. All of this monitoring and research has revealed that Stromboli, for all its apparent simplicity and regularity, is actually a complex and dynamic system operating in a delicate equilibrium. The mountain appears stable not because nothing is happening within it, but because multiple processes are precisely balanced. Magma arrives from depth at roughly the same rate it erupts at the surface. Gases escape efficiently enough to prevent dangerous pressure accumulation, but not so efficiently that the system shuts down. The conduits remain open but structured enough to generate the gas slugging behavior. This balance, however, is not permanent or guaranteed. It represents a particular state that the volcano has maintained for a very long time, but it is not the only state possible. The volcanic record preserved in the deposits around Stromboli reveals periods in the past when the volcano behaved very differently, producing sustained lava flows, explosive eruptions of ash and pumice, and even catastrophic collapses of entire sectors of the edifice. On the northwestern flank of Stromboli, a massive scar descends from the summit craters to the sea, a steep depression nearly a mile long and more than 1,000 feet wide. This is the Sciara del Fuoco, the stream of fire, and it represents both the volcano's primary safety mechanism and one of its most dangerous features. Understanding this geological structure is central to understanding the full spectrum of hazards that Stromboli presents. The Sciara del Fuoco is essentially a horseshoe-shaped collapse scar, the remnant of catastrophic failures that occurred thousands of years ago when entire sections of the volcano's flank gave way and slid into the sea. Geological evidence suggests that at least 2 major collapses have occurred in Stromboli's relatively recent history, perhaps within the last 13,000 years. Each event would have been cataclysmic, sending billions of tons of rock cascading into the Mediterranean and generating tsunamis that swept across the Tyrrhenian Sea. These ancient collapses left behind the depression we see today, bounded by steep walls of volcanic rock and debris. The scar serves as a natural channel that directs most of the volcano's output away from the inhabited eastern and northern slopes. When normal Strombolian explosions occur, the incandescent bombs and blocks they eject typically fall within or near the Sciara, rolling and bouncing down its steep slopes until they reach the sea. Even lava flows, which Stromboli produces occasionally during periods of higher activity, generally flow down this channel rather than threatening the villages. But the Sciara del Fuoco is not a static feature. It is continuously evolving, shaped by the relentless addition of new material from above and the removal of material from below. Every explosion deposits new debris on its slopes. The accumulation of this loose, unconsolidated material creates an inherently unstable situation. The angle of repose, the steepest angle at which loose material remains stable, is constantly being exceeded, leading to small rockfalls and slides that occur almost daily. These minor failures are a normal part of the system, a way the volcano sheds excess material and maintains a rough equilibrium. Occasionally, however, the failures are not minor. The steep slopes of the Sciara, loaded with loose volcanic debris, saturated with heat from the magma below, and subjected to constant seismic shaking from the ongoing eruptions, can fail catastrophically. When this happens, enormous volumes of material can collapse into the sea within seconds or minutes. The December 2002 landslides, which sent approximately 15 million cubic meters of rock and debris into the water, demonstrated this potential with terrifying clarity.
The landslides that day occurred in 2 phases, one at 9 in the morning and another nearly 2 hours later. Both failures originated high on the Sciara del Fuoco, in zones where recent eruptive activity had deposited significant amounts of unstable material. The triggers for the collapses appeared to have been a combination of factors: increased seismic activity associated with rising magma, the oversteepening of slopes by fresh deposits, and possibly the intrusion of magma into the volcano's flank, which would have further destabilized the structure. The material that failed was primarily loose, recently erupted debris rather than solid rock, which meant it moved rapidly and fluidly once set in motion. As the avalanches entered the sea, they displaced massive volumes of water, generating tsunami waves that radiated outward from the impact zones. The largest waves, reaching heights of up to 30 feet, struck Stromboli's northern coast within minutes. There was no time for warning, no possibility of evacuation. The waves damaged boats, flooded buildings, and sent debris crashing through the narrow streets of Stromboli village. Fortunately, the tsunamis occurred during daylight hours in winter, when tourist populations were minimal and many residents were aware enough of the volcanoes increased activity to be cautious near the coast. The death toll was 0, but the potential for tragedy was immense. Had the landslides occurred at night or during the summer tourist season when the beaches and harbors are crowded, the outcome could have been catastrophic. The 2002 event prompted intense scientific scrutiny of the Sciara del Fuoco and its stability. Researchers use a variety of techniques to investigate the structure and behavior of the collapse. SCAR bathymetric surveys map the seafloor around Stromboli, revealing the deposits from previous landslides extending far out into the Tyrrhenian Sea. Some of these deposits, massive aprons of debris stretching for miles, indicate collapses far larger than anything witnessed in historical times. Ground-penetrating radar and seismic imaging revealed the internal structure of the Shara, showing that beneath the loose surface debris lies a complex arrangement of lava flows, older collapsed deposits, and zones of fractured rock. This subsurface architecture controls how failures propagate and determines the volume of material that might be mobilized in a future collapse. The data suggested that while small to medium-sized landslides like those in 2002 are relatively frequent on geological timescales, occurring perhaps once or twice per century, truly massive collapses involving hundreds of millions or billions of cubic meters are much rarer, separated by thousands of years. But rarity does not mean impossibility. The evidence for past catastrophic collapses is unambiguous, and the conditions that produce them still exist. The volcano continues to build itself upward and outward, continuously adding weight to slopes that are already steep and unstable. Magma intrusions into the flanks can weaken the structure from within. Sustained periods of higher eruptive activity, producing more frequent and voluminous lava flows, can rapidly load the Shara with new material that has not had time to consolidate and stabilize. The tsunami hazard from a major Stromboli landslide extends far beyond the island itself. Computer models simulating massive flank collapses suggest that the resulting tsunamis could reach coastlines throughout the southern Tyrrhenian Sea within tens of minutes. Communities in Calabria, Sicily, and even parts of the Campanian coast could be affected. Wave heights would depend on the volume and speed of the landslide, the water depth, and the coastal geometry. But estimates for a worst-case scenario involving a rapid collapse of 500 million cubic meters suggest waves potentially reaching 30 to 60 feet at nearby coasts. Monitoring the stability of the Shara del Fuoco has therefore become a critical component of volcano surveillance at Stromboli. GPS stations measure ground deformation, detecting any acceleration in the outward movement of the flank that might herald an impending collapse. Thermal cameras monitor changes in heat flux that could indicate magma intrusion. Seismometers track both the regular volcanic tremor and any unusual signals that might represent fracturing rock or moving landslide material. Even satellite radar interferometry is employed, measuring millimeter-scale changes in the volcano's shape from space. Despite all these efforts, predicting landslides remains extraordinarily challenging, unlike eruptions, which may be preceded by detectable changes in seismicity, gas emissions, or ground deformation. Landslides can occur with minimal warning. The failure of loose debris on oversteepened slopes can be triggered by events too small to detect: a minor seismic tremor, the infiltration of rainwater, even thermal expansion and contraction. The 2002 landslides, despite occurring during a period of heightened monitoring, were not predicted with any useful lead time. This unpredictability creates a profound dilemma for civil protection authorities. The threat is real and potentially catastrophic, yet the ability to provide specific, actionable warnings is limited, evacuating the island every time monitoring data shows slight anomalies would be impractical and would likely erode public trust when most alerts prove to be false alarms. Yet waiting for unambiguous signals of an imminent collapse might leave insufficient time for evacuation once a landslide begins.
July 3, 2019. The summer of 2019 brought warm weather and clear skies to the Tyrrhenian Sea. Stromboli, as always, drew its seasonal influx of tourists, visitors eager to witness one of the world's most accessible active volcanoes. By early July, the island's hotels and guest houses were full, the restaurants bustling, and guided tours to the summit craters departing every afternoon to catch the spectacular evening eruptions against the darkening sky. The volcano had been exhibiting its typical behavior throughout the spring and early summer. The three summit vents produced their characteristic explosions every 15 to 20 minutes, fountaining molten rock into the air with reassuring regularity. Monitoring data from the Istituto Nazionale di Geofisica e Volcanologia showed nothing particularly anomalous. Seismic tremor remained within normal parameters. Thermal output fluctuated but stayed within expected ranges. Gas emissions showed the usual composition. For all practical purposes, Stromboli was simply being Stromboli, maintaining the pattern that had defined it for millennia. But beneath the surface, conditions were changing in ways not fully captured by the monitoring networks. Deep within the volcanic plumbing system, a batch of fresh, gas-rich magma had begun ascending from the storage chamber several miles below the summit. This new magma carried with it a higher concentration of dissolved volatiles than the material that had been feeding the regular eruptions. As it rose and encountered the resident magma already present in the shallow conduits, the two began to mix, setting the stage for something far beyond the volcano's normal behavior. The afternoon of July 3rd proceeded like countless others before it. Tourists explored the black sand beaches, local fishermen tended their boats, and guides prepared for the evening summit excursions. At approximately 4:46 p.m. local time, monitoring instruments detected a brief spike in seismic activity. A few seconds of intensified tremor that registered on the seismometer stationed around the island. The signal was anomalous but not dramatically so, certainly nothing that immediately suggested imminent danger. Seconds later, Stromboli produced a paroxysmal eruption of extraordinary violence. From the summit craters, a massive column of ash gas and volcanic bombs exploded skyward, reaching an estimated height of more than 6,000 feet in less than a minute. The sound was tremendous, a deep roar that carried across the entire island and out to sea. The ground shook with an intensity that far exceeded the gentle tremors associated with normal activity. The eruption column was dense with debris, ranging from fine ash to blocks of solid lava weighing hundreds of pounds. While the prevailing winds carried much of the ash cloud out over the sea, the larger projectiles followed ballistic trajectories determined purely by physics and the violence of the explosion. Volcanic bombs rained down across a wide area, including regions that had been considered safe from the normal eruptions. Some fell into the villages, crashing through roofs and into streets. Others plummeted into the sea near the coast, sending up enormous plumes of steam. The Sciara del Fuoco became a cascade of fire. Avalanches of incandescent material poured down the collapse scar toward the sea, creating pyroclastic flows. Fast-moving currents of hot gas and rock that raced down the slope at speeds exceeding 60 miles per hour. These flows, while channeled primarily down the Sciara, and therefore directed away from the inhabited areas, reached the coastline and generated small but locally significant waves as they entered the water. On the volcano's slopes, hikers and tourists who had been ascending toward viewpoints near the summit found themselves suddenly in mortal danger. The paroxysm occurred without warning, giving no time to seek shelter or retreat to safety. One hiker, a 35-year-old man from Sicily, was struck and killed by volcanic debris near the summit area. Several others suffered injuries from falling rocks, burns from hot material, and trauma from their desperate attempts to flee down the steep paths. In the villages below, panic spread as residents and visitors alike realized this was not a normal eruption. The sound, the violence, the rain of debris all signaled something unprecedented in the memory of most islanders. People ran from buildings, uncertain whether to head inland up the slopes or down toward the coast where boats might offer escape. The air filled with ash, reducing visibility and making it difficult to breathe. The smell of sulfur became overwhelming. Emergency services responded immediately but faced enormous challenges. The island's limited infrastructure, suitable for handling routine medical issues and small-scale accidents, was suddenly overwhelmed. Helicopters were dispatched from the mainland to evacuate the most seriously injured, navigating through the ash cloud and turbulent air conditions caused by the eruption. Coast Guard vessels moved in to assist in potential sea evacuations if the situation deteriorated further. At monitoring centers on the mainland, volcanologists watched the incoming data with growing alarm. The seismic signals indicated that the paroxysm was not a singular event, but part of an ongoing episode of heightened activity. Ground deformation measurements showed rapid changes in the volcano's shape, suggesting significant magma movement at shallow depths. Gas emissions had spiked dramatically, indicating that the degassing system had been disrupted. The thermal cameras showed that the summit craters were now incandescent with exposed magma at higher levels than normal. The critical question facing scientists and civil protection authorities was whether this represented the beginning of a sustained period of elevated activity or a single, extreme event that would be followed by a return to normal conditions. The historical record offered little guidance. Paroxysmal eruptions at Stromboli are relatively rare, occurring perhaps once or twice per decade, but their patterns are highly variable. Some have been isolated events, followed within hours or days by a return to typical Strombolian activity. Others have marked the beginning of months-long periods of heightened danger, with multiple paroxysms and sustained higher eruption rates. The decision was made to raise the alert level and implement evacuation measures for the most exposed areas of the island. Tourists were urged to leave immediately. Residents in zones closest to the active craters were advised to move to safer areas or leave the island entirely. This was not a mandatory evacuation, but rather a strong recommendation, leaving individuals to make their own choices about whether to stay or go. Many tourists left without hesitation, cutting short their vacations and crowding onto ferries departing for the mainland. But among the island's permanent residents, the response was mixed. Some, particularly those with young children or elderly family members, chose to leave, at least temporarily. Others, whose families had lived on Stromboli for generations, were reluctant to abandon their homes and livelihoods based on what might prove to be an overabundance of caution. They had weathered volcanic crises before. The island had always returned to normal. Why should this time be different? As night fell on July 3rd, Stromboli remained in a state of heightened tension. The volcano continued to erupt more frequently and violently than normal, though no event matched the afternoon's paroxysm in intensity. The summit glowed brightly in the darkness, visible from the mainland coast more than 30 miles away. Ash continued to fall intermittently, coating the island in a fine gray powder that muted colors and muffled sounds. The air tasted of sulfur and stone. The days that followed. In the immediate aftermath of the July 3rd paroxysm, Stromboli entered a period of uncertainty that would test both the scientific understanding of the volcano and the resilience of its small community. The island, normally a place where the volcanic threat was familiar and predictable, had been transformed overnight into an environment where danger felt imminent and unpredictable. Monitoring networks operated at maximum capacity, streaming data continuously to analysis centers where teams of volcanologists worked in shifts to interpret every tremor, every thermal fluctuation, every change in gas composition. The patterns they observed were troubling. The volcano had not returned to its pre-paroxysm baseline. Instead, it maintained a state of elevated activity that persisted day after day, a clear indication that the underlying magmatic system had shifted into a different operational mode. Seismic data revealed that magma was residing at shallower levels within the volcanic conduits than normal. This meant that the molten rock feeding the eruptions was closer to the surface, with less overlying material to contain it and fewer opportunities for gases to escape gradually through the surrounding rock. The result was a higher potential for explosive activity. Each eruption drew from this shallow reservoir, and while most remained within the bounds of strong Strombolian activity, the possibility of another paroxysm remained very real. Thermal monitoring showed sustained high temperatures at the summit vents, with occasional spikes indicating moments when particularly hot, gas-rich magma reached the surface. Infrared cameras captured images of the crater terrace incandescent with exposed magma, something rarely seen during normal activity when the magma column typically remains well below the crater rim between explosions. The heat flux measurements indicated that the volcano was processing magma at a significantly higher rate than its long-term average. Gas measurements provided additional evidence of the system's altered state. The ratio of carbon dioxide to sulfur dioxide in the volcanic plume had changed, suggesting that the source of the magma had shifted to deeper levels where gases remain more pressurized and concentrated. This deep source magma, arriving at the surface more rapidly than usual, brought with it the volatiles that powered the more violent explosions. On July 9th, just 6 days after the initial paroxysm, Stromboli produced another major explosive event. While not quite as violent as the July 3rd eruption, it was severe enough to send volcanic bombs falling across portions of the island once again, to generate pyroclastic flows down the Sciara del Fuoco, and to create a new ash column that rose thousands of feet into the atmosphere. The eruption occurred at approximately 10:17 a.m., a time when fewer tourists were on the mountain, but when many residents were going about their daily routines. The second paroxysm confirmed what scientists had feared. This was not an isolated event, but rather a symptom of fundamental changes in how the volcano was operating. The arrival of fresh magma from depth, its relatively rapid ascent through the plumbing system, and its interaction with resident magma were creating conditions conducive to repeated explosive activity. How long this state would persist, and whether it might escalate further, remained impossible to predict with certainty. Italian civil protection authorities faced a complex challenge. The island could not remain indefinitely in a state of high alert with restricted access and partial evacuation. The economic impact on a community dependent on summer tourism was already severe. Local businesses were losing their peak season revenue. Residents who had evacuated were anxious to return to their homes. Yet the volcanic threat was genuine and ongoing, and the consequences of allowing people to return prematurely, only to face another deadly paroxysm, would be catastrophic both in human terms and for public trust in emergency management. A compromise approach emerged. Access restrictions remained in place for the summit area and other zones most directly exposed to potential eruptions. A network of acoustic and seismic sensors was enhanced to provide as much early warning as possible should another paroxysm begin to develop. Emergency evacuation plans were refined and practiced. Residents were allowed to return but were required to register their presence and maintain communication protocols. Tourism was permitted but with strict limitations and clear disclosure of the risks. Throughout the remainder of July and into August, the volcano maintained its elevated state. The frequency of ordinary Strombolian explosions increased from the normal 4 to 5 per hour to 10 or more. Individual explosions were more energetic, throwing material higher and farther. Lava effusion from the vents increased, with occasional short-lived flows descending the Sciara del Fuoco. The soundscape of the island changed. The regular modest bursts replaced by more frequent, louder explosions that rattled windows and kept light sleepers awake through the night. The psychological impact on the island's residents was profound. Living with Stromboli had always required a certain acceptance of risk, but that risk had been quantified by generations of experience. The volcano erupted regularly, yes, but in predictable ways that rarely threatened life or property. The events of July 2019 shattered that sense of security. The mountain they thought they knew had revealed itself to be capable of deadly unpredictability. Every louder than normal explosion now prompted anxiety. The sound of rocks rattling down the Sciara at night, previously so familiar as to be almost comforting, now triggered worry. Was this just another rockfall, or the precursor to something worse? Scientific teams from institutions across Italy and Europe descended on Stromboli throughout this period, deploying additional monitoring equipment and conducting field studies to better understand what was happening within the volcano. Drones equipped with thermal and gas sensors flew over the summit craters, capturing data too dangerous for human observers to collect directly. Satellite observations tracked changes in the volcano's shape at scales of millimeters. Seismic arrays recorded the complex symphony of signals produced by magma movement, gas release, and rock fracturing deep within the edifice. This intensive monitoring effort generated unprecedented amounts of data, offering insights into volcanic processes that had never before been captured in such detail at Stromboli. Researchers identified subtle patterns in the seismic signals that preceded larger explosions, though the lead time was generally measured in minutes rather than hours or days. They documented how thermal output correlated with degassing intensity and how both related to the frequency and magnitude of eruptions. They observed the three-dimensional movement of magma within the shallow plumbing system, tracking how it filled and drained different conduits feeding the multiple active vents. Yet, for all this data and all this scientific effort, the fundamental question remained largely unanswerable. When would the volcano return to its normal state? The magmatic system operates on its own timeline, governed by processes occurring miles beneath the surface and influenced by factors that remain only partially understood. The arrival rate of fresh magma from depth, the efficiency of degassing in the conduits, the evolution of the physical structure of the volcanic plumbing, all these variables interact in complex ways that defy simple prediction. The summer of 2019 demonstrated both the successes and limitations of the current approach. The monitoring networks detected the volcano shift to a higher activity state and provided data that informed decisions to raise alert levels and restrict access. These measures, while imperfect, likely prevented additional casualties. Had the July 9th paroxysm occurred when the summit was crowded with tourists as it would have been on a normal summer day, the death toll could have been far higher. Yet the monitoring also failed to prevent the July 3rd fatality or to provide specific, actionable warning before either paroxysm. The victim was in an area generally considered safe, following established hiking routes, during a period when the volcano was exhibiting normal behavior according to monitoring data. The eruption that killed him occurred with no precursor detectable by the instruments, no seismic buildown, no obvious change in gas emissions, nothing that would have triggered an alert even if perfect monitoring coverage had existed. This case illustrates a sobering reality. There may be an irreducible element of unpredictability in volcanic behavior, particularly for systems like Stromboli that maintain continuous activity. The background noise of ongoing eruption makes it extraordinarily difficult to detect the subtle signals that might indicate an approaching paroxysm. It is like trying to hear a whisper during a constant conversation, or to see a particular wave approaching across an already turbulent sea. Researchers continue to work on this problem, analyzing data from 2019 and other paroxysmal events, searching for patterns that might provide even a few additional minutes of warning. Some promising approaches involve looking at combinations of parameters rather than individual measurements, seeking multivariate signatures that might be more reliably associated with approaching paroxysms. Others focus on very short-term forecasting, attempting to identify the initiation of a paroxysm in its first seconds so that automated alerts can be issued before the most violent phase of the eruption begins. Living with giants. By late August 2019, Stromboli's activity had begun to gradually decrease from the heights reached in early July. The frequency of explosions declined, their intensity moderated, and the thermal output from the summit vents slowly returned toward normal levels. The magmatic system appeared to be transitioning back to its characteristic baseline state, though scientists cautioned that this process could take months and that sporadic episodes of heightened activity might still occur. The volcano, as always, would operate on its own schedule. The island's residents faced the challenge of returning to normal life after a summer that had fundamentally altered their relationship with the mountain. For generations, the people of Stromboli had coexisted with volcanic activity through a kind of implicit understanding. The volcano would erupt constantly, but predictably, and humans would live their lives in the spaces and times those eruptions left available. The events of 2019 had broken that understanding, revealing that the mountain could turn deadly with almost no warning. This realization forced difficult conversations within the community about whether continued habitation of the island was worth the risk. For some, particularly younger residents with children and opportunities elsewhere, the answer was no. Families who had lived on Stromboli for generations made the painful decision to leave, relocating to Sicily or the Italian mainland where employment could be found and where volcanic eruptions would be distant news rather than immediate threats. Each departure diminished the social fabric of the small community, eroding networks of relationship and mutual support that had sustained island life for centuries. For those who chose to stay, the decision was as much emotional as rational. Stromboli was home in a way that transcended simple residence. It was landscape and memory, identity and belonging. Many could not imagine living anywhere else, despite the risks. They were people shaped by this particular place, by the black volcanic beaches and steep footpaths, by the smell of sulfur and the sound of explosions marking the rhythm of days and nights. To leave would be to lose some essential part of themselves. The economic calculus was also complex. Tourism, despite the risks it posed and the disruption of the 2019 crisis, remained the island's economic lifeline. The volcano that endangered the community also sustained it. Without the steady flow of visitors drawn by the spectacle of accessible volcanic activity, there would be no hotels to operate, no restaurants to run, no guide services to employ local residents. The island's agricultural and fishing sectors, while culturally important, could not support the current population. Either the island would remain a tourist destination, accepting the associated risks, or its permanent population would dwindle to a handful of stubborn holdouts living a subsistence existence. Italian authorities, grappling with their responsibilities to protect lives while respecting the autonomy of communities to make their own choices, implemented new regulations and protocols. The areas closest to the active craters became subject to access restrictions that could be implemented rapidly when monitoring data suggested elevated risk. A system of graduated alert levels was formalized, each level associated with specific recommended or required actions. All guides leading tours toward the summit were required to carry emergency communication equipment and undergo training in volcanic hazard awareness and emergency response. The broader scientific community took the 2019 events as an opportunity to reassess how knowledge about volcanic hazards is communicated to both authorities and the public. There is an inherent tension between providing accurate information about uncertainties and limitations while maintaining credibility and public trust. If scientists emphasize too strongly what they cannot predict, they risk being seen as unhelpful or alarmist. If they project too much confidence in their monitoring and forecasting capabilities, they set expectations that cannot be met and face criticism when eruptions occur without adequate warning. The experience at Stromboli highlighted the need for more nuanced communication frameworks that can honestly convey uncertainty while still providing useful guidance for decision-making. Rather than binary predictions of eruption or no eruption, volcanic hazard communication increasingly focuses on probabilities, scenarios, and time-dependent risk assessments. Rather than claiming that monitoring can predict all dangerous events, the emphasis shifts to explaining what monitoring can and cannot detect, and what precursors might or might not occur before different types of volcanic activity. Education has become a cornerstone of risk reduction strategy. If residents and visitors understand the nature of volcanic hazards, the capabilities and limitations of monitoring, and the appropriate responses to different alert levels, they can make informed decisions about their own safety. Schools on Stromboli and neighboring islands now include volcanic hazard education in their curricula. Tourism operators are required to provide clear information about risks to their clients. Public information. Campaigns use social media and traditional outlets to share updates about volcanic activity and safety recommendations. Yet, education alone cannot eliminate risk, and awareness does not make danger disappear. Stromboli remains an active volcano capable of producing paroxysmal eruptions and potentially catastrophic landslides. The question is not whether these events will occur again, but when. Geological evidence makes clear that the volcano has produced major explosive eruptions and massive flank collapses repeatedly throughout its history. The current period of relatively gentle activity, stretching back thousands of years, is itself an anomaly from a longer-term perspective. Eventually, perhaps in decades or perhaps in millennia, Stromboli will produce an event that dwarfs anything witnessed in historical times. This long-term perspective creates a paradox for risk management. How should authorities and communities respond to threats that are certain to occur eventually, but whose timing is completely uncertain? Evacuating the island permanently would eliminate the risk, but also destroy a unique cultural community and one of the world's most valuable natural laboratories for understanding volcanic processes. Maintaining current policies accepts a level of risk that will, statistically, eventually result in casualties. There may be no perfect solution, only a series of imperfect choices, each with its own costs and consequences. International cooperation has increased in the wake of the 2019 crisis. Volcanic monitoring networks in Italy now share data more systematically with international partners, allowing researchers in other countries to contribute expertise and analytical capabilities. Stromboli has become a testbed for new monitoring technologies and forecasting approaches that may prove applicable to other volcanoes worldwide. The lessons learned here, both successes and failures, inform risk management strategies at active volcanoes from Indonesia to Central America to the Pacific Northwest. The volcano itself remains indifferent to these human concerns and calculations. It operates according to the physics of molten rock and pressurized gas, governed by processes that unfolded long before humans arrived on this island and will continue long after any human presence has ceased. The mountain does not care whether people choose to live on its slopes, does not adjust its behavior to accommodate human schedules or preferences. It simply is, and it does what its nature compels it to do. By the end of 2019, Stromboli had returned to something approximating its normal state of continuous mild activity. The paroxysmal phase had ended, the elevated eruption rate had subsided, and the monitoring data showed no immediate signs of danger. Life on the island gradually resumed familiar patterns. Tourists returned, though in somewhat smaller numbers than before the crisis. Fishermen went out in their boats each morning. Children walked to school along paths overlooked by the smoking summit. The rhythm of explosions once again marked time in its unique volcanic tempo. But something had changed, some loss of innocence that could not be recovered. The island's residents now knew, in a way they had not fully internalized before, that the mountain they loved could kill them. They knew that the monitoring systems designed to protect them had fundamental limitations. They knew that choices made decades or centuries ago by ancestors who first settled this volcanic island had created commitments and vulnerabilities that could not easily be undone. The eternal bargain Stromboli stands today much as it has for millennia, a cone of fire rising from the Mediterranean, exhaling smoke and flame in rhythms that predate human memory. The volcano that the Greeks believed housed their gods, that guided Roman sailors through dark waters, that has drawn scientists and adventurers for centuries, continues its ancient work. Every 15 to 20 minutes on average it erupts. Every day it adds microscopic amounts to its bulk. Every century it reshapes itself through processes violent and slow. It is both monument and process, both place and perpetual transformation. The monitoring networks that now surround the volcano represent humanity's most sophisticated attempt to understand and anticipate its behavior. Dozens of sensors feed continuous streams of data to analysis centers where algorithms search for patterns and anomalies. Satellite systems track the mountain from space, measuring changes invisible to the human eye. Scientists from multiple nations collaborate on research projects that probe the volcano's structure and dynamics with tools that would have seemed like magic to earlier generations. The knowledge accumulated about Stromboli is vast and detailed, a testament to human curiosity and ingenuity. Yet for all this knowledge, the volcano remains fundamentally unpredictable in its particulars. The broad patterns are understood, the general mechanisms clear, but the specific timing and magnitude of individual events lie beyond the reach of current science. We can say that paroxysmal eruptions will occur, but not when. We can identify factors that increase the probability of landslides, but not predict the day or hour of their occurrence. We live in a middle ground between ignorance and omniscience, possessing enough knowledge to recognize dangers but not enough to eliminate them. This incomplete understanding forces a kind of humility that is perhaps appropriate when dealing with forces that dwarf human scale and human lifespan. The volcano operates on geological time, where centuries pass like seasons and millennia like years. The entire span of human civilization on Stromboli, from the first prehistoric settlers to the present day, represents barely a moment in the mountain's biography. We are visitors on a stage where the principal actor has been performing since long before our arrival and will continue long after our departure. The people who choose to live on Stromboli today do so with open eyes. They understand the risks in ways their ancestors could not. They have access to information about volcanic hazards, to monitoring data, to evacuation plans and emergency protocols. They know that the beautiful mountain dominating their horizon is also a potential killer. Yet they stay, bound by ties of family and memory, by economic necessity, by love of a place that is both home and hazard. This choice reflects a broader truth about human relationship with the natural world. We are drawn to places of power and beauty, even when those places are dangerous. We build cities on fault lines and coastlines, farm the slopes of volcanoes, harvest the seas during storm seasons. We do these things not from ignorance but from a calculation, often unconscious, that the benefits outweigh the risks, that life in such places offers something valuable enough to justify the dangers. For Stromboli's residents, that something includes a quality of life found nowhere else. The island's isolation creates a social intimacy impossible in larger communities. Everyone knows everyone, multiple generations interconnected through bonds of kinship and shared experience. The pace of life follows natural rhythms rather than industrial schedules. The landscape, dramatic and strange, provides daily encounters with beauty that many people experience only rarely if at all. The relationship with the volcano itself, despite its dangers, creates a sense of living at the edge of something profound, of daily proximity to forces that reveal the planet as a living dynamic entity rather than a static backdrop for human activity. Tourism has become essential to sustaining this community, creating a complex interdependence between the local population and the global flow of travelers seeking extraordinary experiences. The tourists provide economic sustenance that allows the island to maintain schools, medical facilities, and infrastructure. In return, they receive access to one of Earth's most spectacular natural phenomena, the chance to witness volcanic eruptions in relative safety, to walk on slopes built from erupted rock, to swim in waters warmed by subterranean heat. This arrangement, like the island's habitation itself, represents a bargain with nature. The volcano provides the attraction, the unique selling point that draws visitors from around the world. In exchange, it demands acceptance of risk. Acknowledgement that this is not a theme park with engineered safety, but a genuine force of nature that operates according to its own imperatives. Some years the bargain seems favorable, with steady mild activity that delights tourists and causes no harm. Other years like 2019, the cost becomes tragically clear. The question facing Stromboli is ultimately the question facing all communities in hazardous environments. How to balance the value of place against the reality of risk? There is no single answer, no policy that can satisfy all stakeholders or eliminate all dangers. What emerges instead is a negotiated compromise, revised continuously as circumstances change, as monitoring capabilities improve, as communities evolve, as individual residents make personal decisions about where and how to live. The volcano will have the last word in this negotiation. Human plans and preparations, monitoring networks and evacuation protocols, building codes and insurance policies, all exist at the pleasure of geological processes indifferent to human concerns. Stromboli will eventually produce another paroxysm, another landslide, another event that challenges current understanding and protective measures. This certainty should inspire not paralysis, but rather a clear-eyed recognition of the terms under which humans occupy volcanic islands. What Stromboli offers, beyond its immediate dangers and attractions, is a lens through which to view humanity's larger relationship with the planet. We are not separate from nature, not masters of forces we can control and direct at will. We are participants in systems vastly larger and older than ourselves, systems that operate according to physical laws indifferent to our preferences. Our technology and knowledge grant us some ability to understand and adapt to these systems, but they do not grant us dominion over them. The lighthouse that continues to burn in the Mediterranean, that guided ancient sailors and now draws modern tourists, remains what it has always been. A reminder of Earth's restless energy, of the thin crust separating us from processes that built the planet and continue to reshape it. Every explosion is a small revelation, every rumble a whisper from depths we can never directly visit. To witness these displays is to encounter the planet not as abstraction but as immediate physical reality. Those who live on Stromboli, whether for a lifetime or a summer, enter into relationship with this reality. They accept its terms, adapt to its rhythms, and find within its constraints something worth preserving. Their choice to remain in the face of dangers both known and unknown represents a kind of faith, not that the volcano is safe, but that life in proximity to such power has value sufficient to justify its risks. It is a choice made daily, renewed with each explosion, reaffirmed with each sunrise over slopes built from ancient fire. The mountain will continue its work regardless of human presence or absence. It will erupt through the centuries to come, will grow and collapse and rebuild itself according to patterns established over hundreds of thousands of years. Whether humans witness these processes from the island's slopes or from distant shores, whether they study them with instruments or simply marvel at their display, the fundamental nature of the volcano remains unchanged. Stromboli simply is, and in its being offers those willing to look a glimpse into the forces that shape worlds,